Last time we started with discussing the condition number of the stiffness matrix. That is now the aim, to get an estimate for the condition number of the stiffness matrix, which is here denoted by A. It will be only an estimate from above, so one can argue maybe this is not sharp what comes out, but in fact we will see with an example later on that this is in fact a sharp estimate. And as an auxiliary tool, later on it will become a matrix, so to speak, of its own right. We consider the mass matrix. It's similarly built as the stiffness matrix, but we do not take the bilinear form of the variational formulation, but we just take the L2 scalar product to form the components of the matrix B. So the B always is a symmetric matrix, symmetric, positive, definite. Nothing can go wrong with this matrix. With the matrix A, of course, it depends on the bilinear form small a. The most simple situation, if small a, and with that also capital A, is also symmetric. And we will help us a little bit by using an assumption which basically means that we do not deviate so much from the situation. So that's maybe not 100% satisfactory. So as auxiliary results, we have investigated the following discrete L2 norm, which is composed on our ansatz space by using the corresponding triangulation, the corresponding degrees of freedom situated at the AIs, and we take the squares of the values there, sum over the elements, multiply with dk to the d, sum over all the elements, and take the square root. So it's quite similar to what we did in the beginning, discussing the finite difference method, where we had a similar norm, which we call discrete L2 norm. But in this norm, and in some sense the weight with a d, forget about the dk for a second and take the hk for a second and take hk as h, or more precisely, later on we assume quasi-uniformity, that we have a bound from below and above between hk and h, the maximum of the hk's. Then we would have here the same weighting factor as we had in 2 dimensions. H to the d halves. In 2 dimensions this means h, and that was the weighting factor we used. But what is different here now is that depending on the triangulation, we, so to speak, correct these values squared several times. Because a node belongs to several elements, and without knowing something about the triangulation in the general case, we don't know how often this appears. We have introduced this semi-norm because what are the general assumptions we are doing? We are assuming, that the family of triangulations is regular, that we have an estimate between the rho case and the h case. And the additional assumptions are basically the ones we always do. So we have a continuous and V-elliptic form on a subspace of H1 omega, as usual. So this is a norm. This is just the only question is the definiteness, and that's the uniqueness of the interpolation. And it's a norm of interest because, in fact, it's a norm which is equivalent uniformly in H. That is what's stated here, to the L2 norm. Of course, if I would fix the phi H, then of course every norm is equivalent to every norm. That is not an interesting statement. I have to know what happens if H goes to 0. And in this sense, I have here uniform equivalency. So this is actually L2 norm with which I'm working. And on basis of that, we have seen this inverse inequality, saying that what is of course wrong on a full infinite dimensional space, that we can estimate the one norm by the zero norm we can do here, but to the expense on the finite dimensional space, but to the expense of 1 over h. Okay. The proof was quite as we are used to do them. So we are dealing with integrals. We subdivide the integrals in integrals over the elements, which transform the elements to the reference element, and so on and so on. Somewhere we use Bramble-Hilbert or something like that. Okay, so now two statements are left to be chosen, and maybe you hopefully have forgot the last two sentences, which I said last time, because they were rubbish. I said something which was correct, but I pointed to the wrong statement. What I said was correct not for this statement, but let's go a step further for this statement. So in the end, we want to say something about the condition number of the stiffness matrix. And in the end, what we are going to show is that we can estimate the stiffness matrix by a constant times 1 over the minimum of the hk. So in the quasi-uniform case, this would be just 1 over h to the minus 2. So we have here something like h to the minus 2 times the condition number of b, or in a similar, pretty much related to this estimate is this estimate where b to the minus 1 times a appears. This matrix at the moment, it does not tell us too much, but we will later see in conjunction with time-dependent problems with the heat equation, not with the Poisson equation, but with the heat equation, this matrix will reappear. So, of course, that's only an estimate, and of course we could be totally wrong with this estimate. It could well be that those condition numbers are uniformly bounded in H, and we are only able to prove this very bad estimate. Unfortunately, this is not the case. This is a sharp estimate. If we will look later on very precisely at our example on the rectangle with the Friedrich-Scalar triangulation and so on, so to speak, with our matrix with the 4s and the minus 1s. And for this matrix, we can compute explicitly the eigenvalues, so we can compute everything explicitly. We can compute the condition numbers explicitly in the spectral norm, and then we can compare. And then we see, in fact, really something like 1 over h squared comes out. So this means not only that the system becomes bigger and bigger, which we're going to solve, it's getting more and more complicated to solve it. And that is the reason why the classical iteration methods, which you know or hopefully know from your introductory course to numerics, are not very feasible here. You can use them for very moderate sizes where you don't feel this h dependence in the condition number too strongly, but in principle they have to be substituted by something different. To show this result and to understand it a little bit better, we first show a result about the mass matrix, this symmetric matrix B. And here the result is totally different. And namely, it says we can bound the condition number by a constant, and here I have h over the minimum over the h case to the power t. So that might be something which grows for for families of triangulations which are very highly refined and locally refined in their process. But if we have a quasi-uniform triangulation, that what I mentioned, this word I mentioned already several times, where do we have it? A family of triangulation is called quasi-uniform. So it's not uniform, it's not meaning that all elements have the same size, but it's quasi, nearly uniform, in the sense that the sizes are comparable. Not only from above, trivially, of course, each hk can be estimated by the maximum of h, but also the other way around, in the sense that there is a constant independent of h, such that h, the maximum over the h case, can be estimated by c times the h case. That says there's only a a fixed relationship between the smallest and the biggest element. And this relationship, it might be extreme, so the C might be quite a big number, but this relationship stays the same over the whole sequence of triangulation. It's not allowed that in one point you refine and refine and refine and you do not do anything else in the triangulation for here, which in general would be allowed to do. So if this is the case, if the triangulation is quasi-uniform, then we can estimate the minimum of the H case from below by a constant times H, and that means we have here we can bound this whole thing with a constant here. So it basically says the condition number of the mass matrix is bounded independent of H. So there's no problem with solving systems of equations with a mass matrix. And if we now look at the other statement, having this in mind, sorry, where was it? Having this in mind, was es denn jetzt? Here. Then seeing this factor here, this doesn't play a role. In general, we can assume that this is a uniformly bounded quantity. So, okay, let us prove these assertions now. Okay, we said if a matrix has, this does not apply to all quadratic matrices, but if a matrix is such that, first of all, it has real eigenvalues, which we order by lambda 1 to lambda m, and furthermore, it possesses an orthogonal basis of eigenvectors, or otherwise stated, if we assume that the matrix is normal, symmetric matrices, orthogonal matrices are normal, but of course not all matrices. Then if we look at this Rayleigh quotient, which is just a quadratic form here divided by the Euclidean norm squared, we have a functional which attains its minimum at the smallest eigenvalue, where the smallest, I have to say differently, where the smallest functional value is the smallest eigenvalue and is attained for its corresponding eigenvector, and the maximal functional value is the largest eigenvalue and it's attained for the corresponding eigenvector. So this is now something which we can use for sure for the mass matrix, and for the stiffness matrix, of course, it depends. If we would assume that our stiffness matrix is symmetric, then it would also be symmetric positive, definite, and everything would be okay. And we cheat a little bit by saying, okay, we assume for the stiffness matrix later on that this situation is given, that we can use this tool for analysis. For the mass matrix, we can always use it. So we do so, and by using it, we want to prove this basically uniform boundedness of the condition number of the mass matrix. So let's look at it. So what does it mean? We have a symmetric matrix. We are looking at the condition number with respect to the Euclidean norm. That is, we have the spectral norm of the matrix multiplied with the spectral norm of the inverse, and in the case of a symmetric matrix, that reduces to the norm then reduces to the maximal eigenvalue, to the spectral radius of the matrix. So we have rho m for the b, for the norm of the b, and lambda m, and 1 over lambda 1 for the corresponding norm of a to the minus 1, because a to the minus 1 has just the inverse eigenvalues as eigenvalues. Okay, so we have to estimate this quotient here, and as these ingredients here are the maximum and minimum of those functional values here, we have to find upper and lower bounds. If we find upper and lower bounds and look at the corresponding quotient, we get then an estimate for the condition number here. So we have to deal with this functional given here. So we do the following trick. We introduce here the L2 scalar, this discrete L2 norm, divide by it squared, multiply by it, nothing has happened. then the situation is as follows. Here, this term, let's have a look. Let's first define a function v, which is just the linear combination combined of this vector xi with a nodal basis function. Why do we do that? Because then we have this identity. If we look at the L2 norm of v with itself, this is just xi transpose p xi. Because think of this, plug it in here and here, multiply everything out. Then in the middle you get, so to speak, a matrix which has this color product of the combination of the basis functions. That is what we called mass matrix, and multiplied with the corresponding vectors from the left and the right. So what we have here is just the relation between the continuously defined L2 norm and this discrete L2 norm. We have just remembered that this means that this quotient is bounded from below and above by a constant independent of C. So we only have to deal with this quantity here, with the second factor here. Okay. So, now because of question mark. Okay, this helps a lot. Let's see what this means. I'm now wondering whether we need a further assumption or not. Let's see whether we need it, whether it's here. Yeah, okay, this is this assumption. I remind you this assumption which we have now posed. We now assume, which is quite related to the condition of shape regularity, but maybe it's a totally redundant condition. It's partially redundant in any case. Let's first state it for safety, so to speak. We assume that the sequence of triangulations is such that there is a uniform constant Ca, a natural number, independent of h, such that the amount of elements to which a general node belongs is bounded by Ca. So it's not possible, if I go through the refinement process to the sequence of triangulations, that I get more and more elements accumulating around one point. So this, what is also called the spider web effect, this is excluded. This assumption is redundant in at least in 2 dimensions with triangles, because there we have seen that the shape regularity is equivalent of assuming that there is a uniform lower bound for the smallest angle. But in this case, of course, this transfers directly to an upper bound to the amount of triangles which can share this node. What is open? How is it in 3D or in general D? And so for safety, because I didn't want to analyze how this really, these pure geometrical problems, I took this further requirement, so to speak, as a safety measure. So let's see what we can do with that. So because of this, we have the following situation. We now look at this discrete L2 norm squared we have introduced. And because of this condition here, we can, if you remember the sum, we can reorder it in the sense that we can go over all the nodes in the first loop, and then we have the corresponding h's, hk's, and summed up over all the elements to which this node belongs. But the amount of these elements is bounded by Ck, and the hk is, of course, bounded by h, so we get this upper bound here. The rest, what remains, is just the Euclidean norm squared of this tuple vector here. Okay. But of course, we can also get this lower bound. This is trivial because there's at least one node, a node appears at least in one element, so the others we just throw away from the contributions, we throw away from the norm, and of course we go then from all the individual hk's, we go to the minimum. So we get this lower bound here. So what does that mean? If we now plug this in, these estimates, that means we get an upper bound. Let's first start with this one. If we plug this so this is bounded in any case with a constant. If we plug this in as an upper bound for this part, so the psi norm squared goes away, we are left with this part times some other constant, say, so C1 and C2 denote generic constants, so we get an upper bound of the type generic constant independent of C times HD. But lambda m is the maximum, is the best upper bound, so we have this inequality. And similarly, we get this relation because by this relation now we have as a lower bound constant Zam's minimum. So now we just have to go to the quotient of these things here, and we get a corresponding estimate for the quotient, which we would like to have here. This explains this result here. So now let's go to the stiffness matrix directly. Now, as I said, we have to cheat a little bit. We assume now that the stiffness matrix has real eigenvalues and has a basis. I'm now wondering whether it should be orthonormal or not. Probably not. It's not necessary that's orthonormal. So we only need the diagonizability of the matrix. In any case, we just assume what we need here. We know that is true for sure if we only have diffusive forces, if we have a symmetric stiffness matrix, and in the other situation it's an assumption. Okay, we have looked already at the assertions which we would like to prove. So let's start with it. So we have the following relation. If we would like to look at the condition number of the matrix A, we have to look at this quadratic form. Okay, we see we can write this quadratic form that's now pretty similar to what we had before in this form here. So we bring in this quadratic form with a B as the matrix and take it out again. And we see the second factor we know already. So the second factor is the factor with which we have dealt right now. So this is bounded from above by some constant, so we have only to deal with this factor here. If we are able to deal with this factor here, this first factor here, this first quotient here, then, so we can now see this. Let's assume we get some estimate for this first quotient from below and above in the same manner as we did it right now. Then we can argue, okay, we get an estimate for the condition number, which is based on this, what we get from here, times the condition number of B. We can also argue in a different way. We can say, what we are doing here, if we only look at this factor and forget about this factor here, if we look at this factor here, what we are doing, in fact, we are estimating the condition number now of a transformed matrix by the similarity, namely the matrix B to the minus 1 times A. Why? Look at this new variable eta being B to the square root of psi. So what is the square root of a matrix? Is this clear to everyone? Okay. We are here on the safe. What do we need to do? Define something like a square root, or to define something like a matrix function. The square root is a special matrix function. Another matrix function which you hopefully know is the matrix exponential of a matrix. How can we do this? With the exponential of the matrix, there usually one does it via the power expansion and says, okay, we take the power expansion, we know for the exponential function do the same thing, check what about the convergence radius, and so on. Another way would be we look at the function. Let's first speak only about diagonizable matrices. We look at functions which we can apply to the values of the spectrum, of the eigenvalues. And then you can think, okay, we have then the similarity transformation to the diagonal matrix. With the diagonal matrix, we can do whatever we want then with the function. And then the function of the matrix itself should be just the corresponding similarity transform of this diagonal, say, function applied to the diagonal matrix. What does this mean here? We have to have positive or non-negative eigenvalues here. So in any case, we are here on a safe side because B is a positive definite matrix. And you can do this also a little bit downscaled and say, okay, if I have a symmetric positive definite matrix, then this matrix possesses a unique square root, which uniqueness comes from the fact that we require that this square root is also symmetric positive definite, and the square root, of course, has to fulfill what a square root fulfills, namely this thing here. B to the minus 1 times B to the minus 1 is the matrix. So we have this square root here, and if we want to compute it and we would know the eigenvalues of B, we could do it immediately. And that's also the way it is constructed. And for the uniqueness, as I said, one needs the positive definiteness. That's also clear that we need something for uniqueness. Then even in the reals, we need something for uniqueness. If we do not say a square root is greater or equal to 0, then also 4 has 2 square roots. Okay. So we take the square root for the transformation here. That means this term is just then the scalar product of the transformed variable here. And if we plug this in here, this is elementary computation, then we see here in the middle the matrix B to the minus 1/2 A, B to the minus 1/2. So in fact, we are saying here something about the eigenvalues, and by this about the condition number of this matrix, B to the minus 1/2 A, B to the minus 1/2. But this matrix again is similar to the matrix B to the minus 1A. Because if you transform with the matrix B to 1/2, so I have here the matrix B to 1/2, here the inverse, and you see this adds up to B to the minus 1. This here adds up to the identity, then I'm back to then I get this matrix here out. So independently of what we get out here as an estimate for the eigenvalues and for the condition number, we can either say, okay, by this we have an estimate for the eigenvalues, and by this for the condition number of this matrix, and by this for this matrix, because they are similar, they have the same eigenvalues. Or we stick to this product and say, okay, we get an estimate to what we originally want, and we have to multiply with the condition number of this. This explains these two results. So the only thing is what is left is to show this upper bound here now for this quantity here. Okay, let's do that. Okay, we look at this quantity. What is this? Here, this term psi transpose peak psi, we had already identified as V in the L2 scalar product, and correspondingly, of course, we have here for this term, we have VV in the A bilinear form. So we have to look at this quotient. So we have to get lower and upper estimates. So the upper estimate, the lower estimate is simple but in the sense that, okay, V ellipticity gives us this estimate. This is a trivial step here. And that means we have a uniform lower bound by alpha independent of k for this quantity. This also makes sense if we now, okay, let's think a little bit in these eigenvalues. So what we are going to do is, of course, with all what we are doing, we are approximating PDEs. And of course, we should expect that not only our finite element solutions approximate the continuous solution of the PDE, but also the appropriately defined eigenvalues and eigenfunctions of the finite element of the Galerkin formulation approximates the eigenvalues and eigenfunctions of our elliptic operator. But how is this with the eigenvalues of such an elliptic operator? First of all, now of course we are in an infinite dimensional space. We cannot expect finitely many eigenvalues. We will have infinitely many. And how is this with a vibrating system? There is some ground a basic oscillation. That means we would expect a minimum positive eigenvalue, and of course then all these higher frequencies building up. That means a sequence of eigenvalues going to infinity. Of course, this we cannot totally mimic in the finite dimensional case. In finite dimensional case, of course, we only have finitely many eigenvalues, but we can expect that we have a lower positive bound for the smallest eigenvalue, and also would expect that the smallest eigenvalue then converges to the smallest eigenvalue of the continuous problem, but that is not something we are not investigating here. And we have an increase in the highest eigenvalue, not only in the amount, of course, but also in the value. And this is reflected here in the sense that we see here this lower bound, alpha. And what about the upper bound? What I said also in some sense makes clear that it would not really make sense to expect a uniform upper bound. And what can we do? Okay, of course, by continuity, we can estimate by c times the 1 norm squared. And now by this inverse inequality, we can estimate by the L2 norm. This is good. This we can cancel here. But to the expense of this this minimum to the -2, minimum of the h case to the -2. And this, in fact, gives us these lower and upper bounds for this quadratic form, and by this then the assertions as discussed. And I think this also gives some feeling. It's not clear whether it should be the h to the -2, or maybe it could also be h to the -1. That is still unclear. But that there's something unbounded should appear here, I think, by these remarks should be clear. Okay, so we leave this here. We come back to that when we then I'm not sure whether we can start already today, but at least then on Friday discuss iterative methods. And there are 2 further sections to conclude this considerations about the classical finite element approach with quadrature and the corresponding a priori area estimates. The first, what we up till now we have always assumed that our domain is polygonal. I personally do not think that is a severe restriction. So a piece of metal always is polygonal, and if you would like to have something, and if you think at large-scale simulations. I never, or let me formulate it in this way, I never really worked at an application where I really was forced to have a curved boundary in my domain. But nevertheless, let's discuss that. So now we would like to look at general domains. That means also allowing for curved boundaries. And in conjunction with that, and also to close some gap which we have with the elements based on the unit cube. You remember if we base elements on the unit cube with a ansatz space QP, not QK, not PK, then we till now have the problem. If we only take affine linear transformations, we end up with parallel epipeds. That's not with general, in 2 dimensions, not with general rectangles or hexahedra in 3 dimensions. So we have to allow for more general transformations from the reference element. And this is then what is here in this notation isoparametric element, and these things have some relation. Okay, so I think what we have here I basically said. Okay, let's assume we have a general domain. And we have now nodes which are positioned either in the domain or on the boundary of the domain. And on the basis of these nodes, we have certain geometrical objects, our triangles whatsoever. And then we have a domain omega h, which is just the union of the elements. Up till now, by this assumption of the polygonal bounded domain, we always had omega h equals omega. Or that was one condition for a conformal triangulation also. Now, these 2 domains do not fit together and we, in general, neither the one is a subset of the other or the other way around. Do we have a picture? Yeah, here you see, in a general situation, let's do it with triangles. We position our nodes here, and then we look at the triangles, and here where we have this sort of convex boundary, we get here a triangle, and we get something of the domain which is left out. But here with this more concave-shaped boundary, of course this is now a little bit made up. But asymptotically, we can, under refinement, we can think of these as the generic situations. We get here elements which go beyond of the domain. So the numerical praxis, of course, would be we just do that and don't care. But it has to be clear that we leave, so to speak, our theory, and it possibly also destroys our order of convergence estimates. Let's see what we still can do without doing too much effort. Okay. We look at the simplest example, homogeneous Dirichlet boundary conditions. And this is our ansatz space, and let's assume that our domain is convex. So the situation is always as in this part of the domain. So omega h is then a subset of omega, which is good. And but it's not good enough, because now if we would define our VH in the way we did it till now, only based on the omega h, of course, this would not be a subset of V. So that is the basic assumption of our theory. This is the very heart of the theory, because this conformity, VH subset of V, is the basis for the orthogonality of the error on which everything is based. On which Sayer's lemma is based, everything would break down. So one way in this situation is that we, say formally, extend our ansatz functions. And you see what we're doing. We have here some strange, let's only talk about this simple 2D triangle situation. You see here, we have here some strangely shaped elements, say, which are here denoted by B. And we just add these elements. But we don't want them to contribute anything. So we add them as geometrical elements. We need an ansatz space on them. Okay, we take the 0, the function space only consisting of the 0 function. That is good in the sense that by this way, we are talking about here homogeneous Dirichlet boundary condition, we assure the boundary conditions here. Otherwise, we would have a problem with the boundary condition. And there are none degrees of freedom. So this fits then formally to our theory, and at least we can work as we did up till now. So we get now an extended function space VH tilde, which is now a subset of V. But of course, what is now left is the question: how is it with the approximation power of a comparison element? What can we show for the interpolation operator? And okay, we have to. So this I said already. CS lemma we can use. This I explained how we, so to speak, put this informally. But now we have the problem that we have to look at the interpolation operator, which is extended in the sense that it's on all these sets of the type B. It is just identical 0. Okay, there's nothing, there's only one function there from in the ansatz space, so it's the only possible definition. Okay. So the only problem which is left is now to estimate this interpolation error. And what comes out is a little bit disappointing in the sense, or it shows that also such small changes might change something. What can we do? First of all, how do we estimate here this quantity here? Not a bit confused. Why is here UH? Okay, this is already everything put together in this estimate. Okay, so what we know is this is the quantity we want to estimate. Sea's lemma tells us we can estimate it having a comparison element. The comparison element was this IH tilde of U. This we can again subdivide in the omega H. Here it is our traditional interpolation operator, and in the rest omega minus omega H. In the rest, the interpolation is just 0. So we have here the interpolation error as we have dealt with up till now. We know this interpolation error in this case is H times the 2 semi-norm. But now we have this term left. So we have to know how does the solution behave on this small fringe of moon-shaped elements, so to speak, as under the assumption we are on the space H10 under the assumption that the solution is 0 on this shaped boundary. So we have to know how strongly it grows away from 0, how big this term will be. And of course, this also has to do with the smoothness of the boundary. How large are these moon-shaped elements? And this is a type of result which one gets if we assume, this is much more as we have assumed till now, that the boundary is C2. So locally we can describe it as the graph of a C2 function. Then we can get this estimate here. Okay, this is good because this preserves our order of convergence estimate of the H. If we go on and if we look, for example, as quadratic ansatz functions, then to preserve the order, of course, we have to deliver more. And that is not so easy then. And what comes out is what we then can assure, this is a deterioration of the order H square, which we would have in this case, we can only get the order H to the 3/2. Of course, the question is, and that is always the question, and it's very hard to answer this with theory, maybe some I said already, maybe if then your finite element code is ready, we can do some numerical experiments. Always, if we have the theoretical results that there's a deterioration of, say, an order of convergence estimate for several reasons, for such a reasons, or we have seen already we have a re-entrant corner in the domain, the question always is this a global or is this a local effect? If we cut out a vicinity of the part of the domain which produces this problem and only look at the error at the rest of the domain, do we then see the old order of convergence again? Or is it so that that we have, so to speak, a global pollution in the sense that the order of convergence has gone down everywhere? There are some results in this direction, but they are too complicated to discuss them here. Okay, now let's go on and let's have a look, and then we will see how this again relates to the situation with the curved boundary. Let's discuss isoparametric elements. I said already in the isoparametric ansatz, we have a reference element as we had till now, a k hat, a p hat, a sigma hat for the degrees of freedom. Let's assume that this is of Lagrange type to simplify. But now the transformation is not affine linear. It's not P1 in each component, but it's P hat in each component. That means if we would look at our linear elements in arbitrary dimension, nothing changes. But if we, for example, go to the Q1 element, to the rectangles, to the cubes, then the transformation is not done affine linear, but in each component with a bilinear or trilinear function. And this gives more flexibility, and we will see in a second which types of element, at least in 2 dimensions, can be achieved. The thing is a little bit more tricky now, because we cannot so directly now describe what is the scope of elements we are talking about. With the simplicial elements, in some sense, we did not really need the reference element. The reference element was arbitrary, was in particular simple, but in principle it could also have been avoided. In the simplicial case, we could write down all the bases, taking advantage of the barycentric coordinates. We could write down the basis functions, everything, without going to the reference element. Here it's different. Here the whole thing lives through the transformation of the reference element. And it's not so clear by definition what is the generality which we have achieved. So the amount of elements which we get are just those elements k which can be found as the image set of some f of this type. Correspondingly, the ansatz functions which we have on this element are only defined by back transforming to the reference element and then applying composing with the ansatz functions on the reference element. Because now this transformation not only has linear and constant parts, it also changes, for example, the polynomial degree, bringing that in. And here this is more clear now. The degrees of freedom are just the transformations of the degrees of freedom on the reference element. Okay. The first absolutely necessary thing what we have to assure, of course, is that this mapping F is a bijective mapping from K hat to K. So by definition, it's surjective, what we have here. So we have to find condition such that we don't have situation where in this transformation, these elements, so to speak, like a Klein's bottle or something like that, changes locally orientation and gets, so in principle, all kinds of strange shapes are possible, and of course it also means then elements, points here may appear as images of several points here. So this makes this a little bit more complicated. Therefore, we only look at the very simple situation in 2D. In 3D, it's quite a complicated question, and I'm not sure whether it's really answered till now. So which kind of general hexahedra are possible? You might think of, okay, what is a hexahedron? You can say, okay, a hexahedron is very simple. I take 8 points, put them somewhere in space, and that's my hexahedron. And you can imagine what kinds of very, very strange geometric objects you can produce by that, which are certainly not bijectively mapped from the unit cube. Okay. So, okay. As we always are in a situation where the interpolation problem is uniquely solvable, what we could do is, that's what I just said, we take our 8 points, and when we define the mapping F such that the 8 points in the case of the hexahedron, L points in the general case, 4 points in the case of the rectangle, and we say, okay, we require that the degrees of freedom of the reference element are mapped at those degrees of freedom I would like to have. In each component, this is an interpolation problem which fits, so this defines the F. By definition, this mapping is surjective, but it's not clear whether it's injective. And I forgot to bring it with me. My daughter once built me a general hexahedron by straws. You just take straws, have some ropes inside, and then you can make a nice hexahedron. And if you, this is of course it's a restricted hexahedron because all the edge lengths are the same. But if you now try to transform that, you can imagine what the surfaces do and how they go through each other and things like that. It's quite interesting. Okay. So what can we do with that? The first thing, what is good, and which now relates again to the curved boundaries, is that we can produce curved boundaries by that. So if we would be satisfied with this curved boundaries, so as a definition of the domain, we would have not to deal with these problems which we had before, where we had this problem where omega h and omega do not fit to each other. Look at this specific example. We have a triangle now with quadratics, with 6 points, and with the quadratics, and we don't take the linear transformation up till now, which of course would only produce a triangle. But now we take the isoparametric transformation. That means we now transform correspondingly in each component by a quadratic polynomial. And this means we get corresponding, in general, those quadratic shapes. We can also, now you would say, okay, this may be too much I would like to have. If this is supposed to be a boundary element, this looks okay, but why this and why this? But of course, this can be, enforced by just taking those points on a straight line here. We just said, okay, let's forget about this injectivity problem for a second. We just have to fix those points. Then we have uniquely this mapping. So we could take, so to speak, points on a parabola. If we would say this is good enough for the boundary of our domain, and the points here we could take on straight lines, and then we would get an element which has one curved boundary. So that would be another way to deal with curved boundaries. Okay, maybe this, we can also think of subparametric elements. Maybe I skip this. This is all set. This I already just started to discuss. Now let's look at general quadrilaterals and general hexahedra. That is, what is a general quadrilateral? I just have 4 points in the plane, and the corresponding and the object is defined by this bilinear mapping of the unit square bilinear to this element, and correspondingly then in a 3D. So let's see what happens. So this is the situation we are looking at. We have now, it is still defined in general dimension. We have the unit cube in general dimension. We have this ansatz space, the Q1, so the bilinears, trilinears, D-linears. And so what does that mean? All our elements are such that if I look at face of an element, in particular at a face S hat of the reference element, and I restrict my ansatz space, and I restrict my degrees of freedom, then I get again an element 1 dimension lower. That means the faces, they are determined by the nodes which are in. What does that mean? That means in 2D, I only get straight lines as faces. In 3D, I get curved faces. Because in 3D, I have then 4 nodes, and in general, this is too much for a plane. I have to have a curved face then. Here I have only 2 nodes. This is still okay with a straight line. So the question is it possible to map in this bijective manner, in a bijective manner with a mapping of this type of the reference element of the unit cube, say, to a general quadrangle, Viereck? And the answer is basically yes, if we restrict ourselves to convex quadrangles. You see, in principle, this is now a nicely shaped quadrangle, but I don't have a picture probably. But in principle, everything is possible. If you zoom, let's move this point in, and you see what kinds of strange quadrangles then appear. And the assertion now I'm going to prove is when I restrict myself to convex quadrangles, then it means that that is the situation which I get as images under bijective mappings of this type. Okay, let's collect a few things about these quadrangles, what we have here. So we have 4 nodes. Where is it? Going back to this picture, unfortunately, we only have here 1 beamer. We have these 4 nodes, A1, A2, A3, A4 in counterclockwise. And here the corresponding reference nodes in the reference element. And we assume that they are not, we will later on come to this convexity assumption, but first we assume that they are not all on a straight line. Of course, we do not assume, we want to assume that this quadrangle does not degenerate to a straight line. Okay, that means these A1, A2, A3 are in general position in allgemeiner Lage, that is, or otherwisely stated, the connection vector A1, A2 and A1, A4 are linearly independent, that is, they produce a triangle as their convex hull. So we have here a triangle A1, A2, A4. This I denote with D. And of course we know we have our affine transformation, and we know how this belongs together. So we have the affine transformation which maps the corresponding reference triangle, A1 hat, A2 hat, A4 hat, to this triangle here. And we know this relation between the volume of the triangle and the determinant of this transformation. Okay, now we have this fourth node. We have the A4 hat and the fourth node is the number 3. So we have the A3 and the A3 hat. So this A3 is a general node. So in general, it will. So what do we have? We have this mapping. Now, first of all, this affine linear mapping, not yet this F mapping. This affine linear mapping. It gets a name. Let's see what the name is. It gets the name FT later on. So we have this mapping FT mapping this triangle to this triangle. Of course, this mapping maps not only the 3 nodes of the triangle, but every point to something. In particular, the A3 hat. So there's some image of A3 hat somewhere. In general, that will not be A3. It will be some other point. So this point gets a name. It's A3 tilde. And let's see what we have. We have here the triangle which we really want to have. Here we have the reference triangle, which is amended by a 4th node, and the 4th node is now the back transformation of the A3 by this affine linear mapping here to this side. So this is now a special rectangle with 3 fixed nodes and 1 general node here. And we know this between this situation and the general situation we would like to look at, we can do this step by an affine transformation. This means the total transformation we would like to see, the total bilinear transformation we would like to see, can be possibly decomposed in a bilinear step, but now not between this element and this element, but only between this element and this specific element. And if we could do this, then we can go further to complete the whole thing just by this affine transformation. So we only have to look now for the existence of the FQ and characterize where the FQ exists as a bilinear transformation. So this thing always is bijective. So if we do this decomposition, of course, this F is bijective if and only if this FQ is bijective. So now we require a little bit more. What we require is that, so the differentiability is not the problem. Of course, our functions are differentiable as often as we would like. But you remember how this is, maybe with a theorem of about implicit functions, which tells you, can I invert a functional relationship? And you need, in multi-dimensions, you need the invertibility of the Jacobian, of a Jacobian. In general, of course, we can characterize the invertibility by the determinant condition. And what we require is that the determinant everywhere has the same sign. It's either positive or negative. This ensures, as a consequence by the theorem about implicit functions, that locally the function is invertible, ensuring the injectivity. But it's a little bit more than just requiring that the function is injective. So what we actually are going to characterize is this condition. When can we assure that the determinant of the transformation function, and that is, of course, the product of the determinant. So we have the composition, so it's determinant is the product of determinants. Here we always have something positive, that's the determinant of B, so it's only the question of the determinant of the DFQ. So, and this is the statement. And this is quite a nice statement, in particular as the proof has a small surprise. So the statement is we are considering a general, in 2D, a general rectangle, Viereck, with the nodes A1 to A4, counterclockwise oriented. Then we have the determinant does not vanish everywhere on the reference unit square, if and only if its determinant is positive. It's clear it has to be positive or negative. We cannot have a sign change that is in contradiction to the, what is it, mean value theorem. Is it this? No, not mean value, Zwischenwertsatz. What is Zwischenwertsatz in English? Maybe intermediate value theorem. I don't know what Zwischenwertsatz now means in English. And this again is equivalent to the fact that the Q is convex and does not degenerate to a triangle or to a straight line. Okay, now the proof. This I said already. We look at the Jacobian. The Jacobian is the product of the Jacobians of the two transformations. The one of the linear ones is just a B. The determinant is then the product of the determinants. This is a positive number. We only have to look at this number. So we write down first our transformation. So this is our transformation. Our transformation is bilinear. This you see here. Oops, there it is. This you see here. It's not linear, it's bilinear. And what does it have to have? It has to fix the nodes in the reference element with the indices 1, 2, and 4. So all the nodes which have at least 1, 0. But if I have at least 1, 0, this term vanishes and the node is fixed. And the other node, which is just the node with the index 1, 1, 1, 1, has to be mapped to A3 tilde. And that is also what happens here. A3 tilde minus 1 plus 1. Okay, so this is the function. Now I have to decompute the partial derivatives to set up the Jacobian, and then I have to decompute the determinant of the Jacobian. Not very demanding things to do. But what do we expect? What do we expect? What do we have? We have here bilinear functions. So the products, the derivatives in general are again bilinear functions or linear functions. But then look at the definition of determinant, in particular for two components. Then we take products again. So in the end, we expect for the determinant that a bilinear function comes out. And if this would be, then it would be quite difficult, because we would like to say something about the sign of this function. And but the surprising effect is this result here, saying the determinant is just a linear function. There are bilinear terms, but they just cancel if you do the computation. And now it's quite simple. It's an affine linear function, and we are on the unit square, and we want to say something about the sign, but an affine linear function assumes its extrema at the nodes, so we only have to look at the nodes. So what is at the node 0? There's the 1. At 1, 0, we get the A3, 2, and so on, and so on. We get these three values. So you see, the 1 says if we have a uniform sign, the sign can only be positive. That is, the requirement is that these three things here, so the component of this specially transformed A3, so this put back with a affine transformation. This node A3 in its two components, they have to be positive, and they have to be above. That is, then we have this condition. This tells us they have to be above the straight line connecting the 0, 1 and the 1, 0. And this is just the convexity. Let's look at the picture. This was this node here about which we're talking about. So the first thing said the components have to be positive. It should not be here or somewhere. And the next thing, it should be above this straight line. So it should not violate the convexity, not diving in here and producing a corner like that. Okay, that's it. Okay. Concerning the order of convergence things, we can do the same thing with these isoparametric elements as we did till now. It's a little bit, and with respect to the evaluation, it is seemingly a little bit more complicated, because now if you think about the assembly process, think about the back transformation of the integrals with derivatives to the reference element. Then we had to transform the derivatives and always got the Jacobian in. In the affine linear case, the Jacobian was just the constant matrix B. Now it's a variable matrix. But it only tells that it's even more complicated or even more impossible to evaluate these integrals exactly. If you apply quadrature rules, not so much changes. Quadrature rules just means instead of having these fixed terms b with the b, we have now these variable terms with the d, f, and so on, and we have to evaluate them at the quadrature points. That's all. So in praxis and also in theory, not so much changes. Okay, so I just need more time than I expected, but we have still some time to start now with this last aspect of the first approach to finite element theory, that is the maximum principle. So remember our discussion of the finite difference method, and in the finite difference method we said we had this very classical theory of everything pointwise, of pointwise consistency error. The price was enormous regularity to estimate this. And then we said in conjunction with that, we need corresponding stability also in the maximum norm. And this we can get from the inverse monotonicity of the matrix. And the good thing of the inverse monotonicity is not only that it gives us a way to prove orders of convergence, as in this case, but it also gives us qualitative properties of the solutions as they should be. It prevents us from overshooting and undershooting, from unnatural negative values if something is supposed to be a concentration or things like that. So it's of interest of its own if a method preserves the maximum principle, even if we have shown convergence in other norms and with other methods already, as we have done it here. So we don't need the maximum principle here to show an order of convergence. We could also do, but it was, at least if we do it in a simple fashion, it is suboptimal what we get out. We are then, related back to the interpolation error, but the interpolation error is only of order h, which is okay for an H1 norm estimate. I'm now speaking about linear elements. We will here only speak about linear elements, and in particular on 2D, that only about linear triangles. But of course, we would expect more. We would expect, as we have seen already also in the L2 norm, we would expect not h, but h square for the linear ansatz for triangles. And the optimal estimate for the also in L infinity norm in this situation would be also an h square estimate. There are some tricky things, whether this holds or holds not. Sometimes an L-infinity estimate is disturbed by some logarithmic term, which you can hardly see numerically, but of course, theoretically, it makes a difference. But this is not the point here. The point is really this qualitative properties of the solution, which comes with the validity of the maximum principle. And remember how we did this. We really looked at the matrix itself and had several properties of the matrix, sign properties, sum properties, which ensured then this that the matrix was an M matrix, a special form of an inverse monotone matrix. So let's do the same thing here again. So as I said, in more than 2D, this is a very complicated question, also not fully solved till now, so we restrict ourselves to 2D. We have a polygonally bounded domain. And first we look at XH. You remember this was this finite element space which was a little bit larger, at least in the situation where we would have some Dirichlet boundary condition, because it also takes the Dirichlet nodes as degrees of freedom. And we restrict ourselves, so we're going back to the very beginning, we restrict ourselves only to the Poisson equation first, with some right-hand side in L2. But the difference, of course, now you can ask yourself, what is the difference to what we did till now? This is just what we did is already in the finite difference method, but in the finite difference method, in the language of the finite element method, we did it only for the Friedrichs-Keller triangulation. And the question is now, if we now have a more general unstructured triangulation, because our domains demands for that, what kind of conditions are necessary to ensure the maximum principle, which we have seen already in a special case? So we have seen already, if you want, in the special case, if I do the Friedrichs-Keller triangulation, if I have elements which have one right angle and two acute angles, everything is okay. Can I allow for more? That is the question. Okay, so first we write everything again in this algebraic structure, that we really have the matrices we have to analyze. So this is now exactly as we did it in the finite difference situation. So first we count all the nodes which are in omega, which are on the boundaries which are not Dirichlet boundaries, so we come up to M1. Then we count the nodes, so this gives then a solution vector UH. And then we count the nodes which are on the Dirichlet boundary, then we go from M1 plus 1 to M1 plus M2. This gives an additional vector of prescribed values, UH hat, and this together gives the long vector UH tilde, the full solution vector with the Dirichlet nodes. And you remember hopefully also this structure from the discretization. So we have here our, if we now do as I have advised to do it for the assembly process, so we assemble the stiffness matrix first ignoring the Dirichlet degrees of freedom, and then we bring the Dirichlet of freedom to the other side, then we have exactly this situation. We have here the stiffness matrix in a quadratic in M1 degrees of freedom. We have here a matrix of the same build, but now a rectangular matrix, M1 rows, but only M2's unknowns, as many as we have Dirichlet's values, and here the UH hat, and here the corresponding right-hand side F. So this is the algebraic picture, and in this algebraic situation we would like to see the maximum principle, and we have seen we can relate this to a certain amount of sign and some properties of the matrices AH and AH hat. Unfortunately, if I would have two, it would be very helpful to now have two projectors. And maybe you can remember a little bit the situation as it was before. to make sure that I do not miss too much, I go to the corresponding point way back. It was, I think, 132 in the English edition, and as far as I remember, 128 in the German edition, with the corresponding variation with a star. So let's go through the properties a little bit, what we need. Let's do not look at all at the moment. So what do we need? We said, okay, we would like to have that the diagonal elements are positive. That's no problem here. We would like to have that the non-diagonals are non-positive. That is a question. And then we had various sums and irreducibility conditions or weakenings of these irreducibility conditions. So let's first concentrate on this non-positivity condition for the non-diagonal elements. Okay, so to do so, we have to look at the entries here, and we know that the entries, which is just written down here, so gradient phi j times gradient phi I, this restricts to the integral over the intersection of the supports of phi I and phi j. And we know the support of the nodal basis functions are all the elements which contain this corresponding node. That is, here we are looking at elements which have both the node AI and AJ. We are speaking about triangles, so we have either the situation there are two of those triangles, it's an interior situation, or it is just one triangle, if we are talking about a boundary, an element which is at the boundary of the domain. So we could now do two things. We could now go over all those elements and assure that the sign of the contributions from the element is non-positive. Of course, then also the sum of the two contributions is also non-positive. We could do it a little bit more precise and really look at the sum, meaning that there could be something which is positive if the other contribution is negative enough. So let's first start in really exactly computing this contribution at an element k here. As we said, we have one or two of these elements k. And the assertion is, if I have an arbitrary element k, and I have the two nodes A1 and AJ belonging to k and a third node, then this contribution here, this off-diagonal contribution in the stiffness matrix is just -1/2 cotangent of an angle, alpha ijk. This is the angle in the element which is opposite to the edge with the vertices A1, AJ. So, okay, so we would like to have that this number is negative. That was the strong assumption. That is the assumption which we have to do at the boundary where we only have one element. Or when I say non-negative, negative, I always mean non-positive. So we would like to have a corresponding sign greater or equal to 0 here for the cotangent. And that means this gives us a requirement on the angle. This tells us that the angle has to, the maximal angle which is allowed here is pi/2. We should have a picture. Oh, here's the picture again. Let's see again the geometric situation. Here we have this element. Here we have AI, AJ. Here we have the other node denoted by AK, and here we have this opposite angle. So that would be, if we only would rely on this result alone, then the requirement would be the angle has to be at maximum pi/2. So we cannot allow for obtuse angles. For pi/2 we get the contribution 0, And you remember we have seen this in the computation of the 5-point star. In the 5-point star, how was this? In the 5-point star, as 5-point stencil, we had here this node. Then we had here the corresponding elements which we had to consider, and the elements we had to which this belongs were all those here. That's correct, yes. Oops, this here not. So in principle, we could have a contribution here. But we computed then, okay, we don't get a contribution. We don't get a 7-point stencil, we really get our old point stencil. But this is exactly the situation. Here, and the opposite angle is pi12. Contribution 0. This was not by chance, we now recomputed this. So this is the extreme case which is allowed. As I don't have time to do the proof today in detail, what we just do is we go on and let's look at the consequences of this result. Because this is now not only an estimate, but really an identity. We can, of course, go on and now compute what the sum is of the two elements which have these two nodes. And this is what is in this formula. So what do we have to do is we now have to sum these two quantities. So we have an angle alpha ijk and one of the other element alpha ijk dash. And what do we have to add? We have to add minus 1/2 cotangent of the one alpha plus cotangent of the other alpha. But the sum of the cotangents is thus just this quantity. There's no miracle with this formula. It's as easy as the 1 million question in Wer wird Millionär. It's as easy. So you have the cotangent. You have cotangent. You have cosine over sine plus cosine over sine. You bring it to one fraction. Oh, let's do it. Let's earn 1 million. Cotangent of alpha plus cotangent of beta. What is this? This is cosine of alpha over sine of alpha plus cosine of beta over sine of beta. And of course, this I now bring sine alpha, sine beta. Then I have cosine. You should not discuss now that 26 comes out. It is so obvious. This is so obvious. It's a shaming, this question. So what do we have? Cosine sine beta plus cosine beta sine alpha. So, and now what is this here? What I can write for this here? This is... So what is the cosine is the real value, the real part, and the sine is the imaginary part of the e to the I x. And how do we get the imaginary part? Reals times imaginary plus imaginary times the other way around. Reals times imaginary plus imaginary times real. So this is just sine of alpha plus beta over sine alpha sine beta. And hopefully this is what we have here. Yes, this is what we have here. So the critical thing with the sine is this part here. And you see, the only thing which is not allowed to happen is that the sum of the angles which are opposite. So the situation is now the following. So these are the two triangles. These are A1, AJ. You see here I have a very obtuse angle, I get a positive contribution from this element. Here I have hopefully a much stiffer, a much more acute angle, such what I have to have is that the sum of those has to be below 2 pi. I have to prevent that the sign becomes negative. So this is then the geometric condition we get in if this lemma is correct, and this we will then hopefully prove next time.